So let me introduce to you David Ben Shimol, CTO and co-founder of Grappa. He also has a ton of experience at Google X, and now moving into blockchain. And he is here to talk to you about messaging infrastructures in the context of blockchain.
Hey, how you doing? Cool. So I'm the CTO of Grappa indeed, and Grappa, we're actually building a digitized people's reputation, basically, the ability to know what people's achievements, skills, and background is, and communicate with them on the context of that. A little bit about me, I went to the Technion, actually went to medical school, but have like 20 years of experience as a software developer. I've been to Google X, mostly doing machine learning applications in healthcare. And I actually find a lot of similar things between machine learning, on the verge of game theory and blockchain and, unified economies that you can find on blockchains. So I'm going to start by just showing a few slides that give you kind of an impression of what we're building. I'm going to start with that, just because this has been kind of some of the inspiration for the product, because Web3 is kind of filled with this type of examples, right? Like basically a unified singular achievement that you want to convey, but it's really hard to convey something like that through like a regular resume, even a LinkedIn, and you probably should, because this is like a 12-year-old boy that had such a great achievement. And you want to be able to atomize that and actually communicate on top of that. So on the context of that, a lot of companies are actually trying to solve the future of work, trying to kind of make resumes concise and machine readable in a way that allows you to connect them with opportunities. We actually took like another approach. We don't think it's something that will be solved by machine learning, AI, as intelligent as it may be, probably like it's going to be part of the solution. But most of the solution is actually incentives. It's actually making sure that the same interactions you have in real life can happen online, can happen on the digital realm, with incentives that are aligned in order to create value discovery. So for example, a skill, an achievement will actually receive the credit it deserves, and you'll be able to communicate with one another on the basis of things you've done, skills you've had, and people who are vouching for you as a certain skill holder. So blockchain is obviously lends itself immediately to such a problem, like incentivizing people based on tokenomics, economics, and game theory. And to the topic of this conversation, I'm going to start that we want to build trust in the system by allowing people to actually vouch for one another. And on that context, we want to be able to communicate, like I said, on those contexts. So obviously, discussion about messaging, but messaging in a different way that always takes something into account, that always have like a value attached to it. So that's kind of where we're starting. And don't worry, I know it sounds like weird, but I'm going to give another example of like how things work in a more like mechanical way. So for example, this is Jane, and Jane has a lot of achievements. And she has achievements that are structured, like a master's degree, and you have achievements that are more personal, like she's been chosen by a VC to be the top 10 up and coming, very abstract, but actually allows you to be communicated as a badge. And the way things work from the engager perspective, engagers in our world is basically recruiters, people who want your attention. It allows the recruiter, the engager, to actually buy a portion of Jane's time in the form of a message. So basically you buy it with tokens, you buy it with something that builds a reputation. And you see that the unique part of this system is that value actually flows back to everybody who have ever vouched, everybody who actually issued credentials to Jane in a way that builds their reputation as well. So it kind of connects to what I said in the beginning, that machine learning is very similar, because you kind of put a lot of the gradients together in a way that converges to a solution, converges to value discovery. But if you see this as kind of a primitive example of that entire system, you see how the value actually flows in the right direction, much like it will flow in real life when you are vouching for a friend to a certain position, or you're vouching for a friend in general. You get some of that reputation, you get to build some of your network and scoring. And the way we treat that is very similar to how we treat airline miles. You can, I mean, they are value, they are tokens, they have some kind of utility, but they also have utility in a way that allows you to build your status in a certain airline, show your kind of, I would say, mileage and kind of commitment to that institution. And if you kind of look at it with like half an eye, you see that it's very similar to how PageRank work in general. PageRank is kind of an algorithm that looks more on who points at you than actually what you are showing in your own page, and allows you to discover the right things that are interesting and the true value. Yeah, and if you want a more like visual example, this is how it looks like in the actual system. You see this is like an inbox that people actually get messages, but the messages actually come with tokens. Actually, they are coming with some kind of assessment of how much that recruiter valued your time. And it's not something that allows you to get rich or get like an extended salary. It's something that allows you to discover what type of reputation you have. And more than that, allows us to understand what are the badges, or the system to understand what are the badges that are important in general. So with that, let's get to the more technical part, which actually is that we want to build. Part of this system is actually obviously a messaging system. And like I said, it's a messaging system that has something different about it, right? First of all, it's on Web3, but there needs to be a reason for it to be on Web3. So this is like a general kind of review on what a messaging service is in general. And going through that pretty quickly, you have to have an identity. Like WhatsApp, for example, has phone numbers as identity. The post office has addresses. Post office addresses as identity. You have to have a cipher. You have to have some way of masking what you're writing, so it will actually arrive to a certain individual and not be readable by everyone. There needs to be a security, a way for you to safeguard your ability to get something very personal. And eventually there's storage, like post office have SACs for that. Blockchain obviously is doing it in a different way. Magic is something I kind of reserved for the reason of why we're actually doing it on Web3. Because there are a lot of very adequate solutions out there for messaging, and you also see a lot of very busy space of Web3 messaging. If you don't have a reason to do it on Web3, much like everything else, that added complexity is not needed. So we actually have a very good reason to do it on Web3, and that's why we are building it somewhat from scratch, and I'll kind of walk you through it. So let's start with identities. Identities, basically, I can argue that a blockchain is a messaging service in a way. Like you have verified identities, you have identities that you can verify they are the source of the transactions. But if you think about it, transactions are basically messages. They're messages with instructions, but that's what they are. And that's one thing you're basically getting for free in Web3 if you think about it. What's missing is actually the targeting mechanism if you want to target a certain individual. But you see that messages are coming from the users to the public, and they're coming the right way. They're coming with like a stamp of approval on it that they actually came from the right person. Now, what's missing, like I said, is Cipher system basically has something that allows you to get some kind of privacy, or basically a targeting mechanism. That certain user can only open a certain message because it's addressed to them. But when you think about it, the tools, the components to actually achieve something like that is actually already there. Everybody has a private key, everybody has a public key. What you don't have is basically the security, because nobody wants to use those to decrypt messages. So usually what a lot of the services that you see now on Web3 messaging, XMTP, Dialect, the new company every day. So basically what they're doing is taking your private key and creating a proxy of that can only be created from that original private key. And when you have that, then you trickle down, but you basically have built a traditional messaging system that allows you to transact based on a cipher. So just to kind of wrap that up, basically you're creating something that is unique to a certain individual, but then you use that to generate a pair that you can then use in order to send and receive messages. And storage, in blockchain, we're obviously limited on that, so that's where kind of decisions around like how you actually structure the blockchain comes into play. So most of the solution actually build their own, for various reasons, but that too actually build their own kind of blockchain. Also to broadcast the public key that you just created. And that drives a lot of decision of off-chain, on-chain. And we actually chosen to be on-chain for a reason that is why we actually wanted to do it in Web3 from the beginning. So the reason basically that everything is working on blockchain is our ability to distinguish between people based on value. I'll rephrase, not people, but basically the skills and achievement that they have. And it's kind of, you take the sum of people's skills and achievements and you showcase them based on their reputation, but then it's a supply and demand kind of thing of like how many recruiters actually want to contact you, how many recruiters actually want a piece of your time. And I know it sounds kind of weird, but when you think about it, everybody here has a LinkedIn profile, and when people send you messages on LinkedIn, they actually pay quite a lot of money to LinkedIn. So the average can be up to $5 per message, basically. And obviously that money doesn't come to you. That value is not very detrimental, but it's not coming to the person who actually is building the profile, who actually building the journey behind the profile. So that's what we want to achieve, and we want to achieve it in a way that allows us to, like I said in the beginning, get alignment of incentives. Okay, so let's get to the more kind of highly technical things, I guess, at the demo problem that we've kind of brought. So we have a system that basically is working. It's working with much like you would expect from a messaging system with the private keys, public keys that are being generated from your unique wallet. But then you basically need to build something that will operate on-chain. So this is a very highly reduced version of that architecture. And we want to kind of push a lot of the calculations to the actual client. So the best tool that allows you to do that today is zero-knowledge proofs. And I'll expand it a little bit in a second, but kind of to give you the general kind of architecture of the system. You see that for sending a message, there is private data that you want to keep to yourself. You want to keep the receiver. You don't want people to know who you're sending a message to. You don't want people to actually, obviously, read the message. And you don't want people to have your private key. So this is private data that you're keeping away from the world. And there are obviously public data, for example, the encrypted version of who you're sending the message to. And we do it with salt just to avoid repeatability. You have the sender's address in order to get replies. And you have obviously the encrypted message, which is public. But the unique part, and actually where you use zero knowledge, is generating the snark. I'll expand a little bit in a minute and how you actually generate a code that lives in the client. But the added value here is that you're doing that on your machine, and all you need to send to the chain is a succinct, basically a short proof of the fact that you did all the right stages, that you actually have a user, that you actually have a valid private and public keys, and that you actually are sending it to a person that is valid. And And the way to do it on the backend is basically reviewing everything and verifying everything, but you lose the privacy. You know now who you're sending the message to. So the way it works with two contracts. One contract is very simple, actually. When you send the message, you just send the proof. There's a verified proof that gets referred to a secondary contract. And if everything works, you're basically sending the message. You post an event on chain that has basically all the right ingredients to enable the receiver to decrypt the message and read it, and also send back a reply. And where the zero-knowledge tool comes into play is actually generating what's happening here within the verified proof. So we're using a tool called Circum. It's basically converting textual, like basically not textual, but like code into mathematical equations, polynomial equations. And what that contract will do eventually is just solve those equations and give you a lights up, a thumbs up if you actually, if the proof is actually valid. And that's get auto-generated. I put a bit, kind of a snippet of code down here that actually tells you pretty trivially how you actually deploy those contracts. And the reason that they're being deployed in Cascade is because you first deploy the controller. First deploy the verifier, but then actually deploy the controller that needs to point to the verifier. If anybody has a question, I'd be happy to kind of stop and answer. Just raise your hand. I hope I'll be able to see. Okay, so a little bit about ZK Snarks and why we're actually using it. I'm not going to expand too much because we've seen a very good deck by Howard from Elio that actually went into depth of why you're using zero knowledge and all the kind of intricacies and the details of it. What I want to get is actually pretty applied with the knowledge and actually show you how it works in real life without using any kind of proprietary tools. What the benefit we're getting from it is obviously scale and privacy, and the scalability that you're getting by allowing people to do all of the work that you should have done in the server, but doing that within their browser. I'll try to show like an example of the tool we're using. So the tool is called Circum, and Circum is basically a tool that has been around for like 4 years now. Is it big enough? Probably not. But it's a tool that basically is very simple in the way that code is written for this tool. You've specified the inputs and outputs, and then you specify the logic that needs to come into play in order for you to validate the proof. It's too small, so I'm going to show it off the screenshots. And it starts from here. I hope this is kind of big enough. Probably not. Let me press this. Trying to assess the. Okay, so this is how a proof on Circum looks like. You see what you're getting in the beginning is basically the ability to specify inputs. Some of the inputs you don't want other people to be able to see. Some of the inputs you actually are public because they need to send some instructions to the actual contract. And we start by actually specifying those. You're specifying your private key and the receiver private keys. We have a key set that's a token and a message. The token actually just specify who you're sending the message to. And then there's the public key and private key of the message itself. The reason it's separated is because you want to be able to delegate the token understanding to a third party if you want to get push messages or things like that. Obviously, you don't want to delegate the message reading because then people will be able to read the messages themselves. So it starts by basically saying, I show it off of here. Okay, but it's like, by basically asking, is it a valid pair of private to public? So we're actually using a function that just verifies that if you take the private key, you're actually derivating the right public key. So this is a denotion for Circum that says I'm going to put this value into that function, but then I'm actually going to verify later that the function actually went through and actually proved that specific statement. So these two actually verifies that we have a valid pair. And this actually calculates the shared key. I'm going to go in very soon, very quickly about like Diffie Hellman and why you actually want to do that. But for now, it's like basically you want to multiply the receiver's public key with your private key in order to create a shared secret that you can encrypt things based on. So yeah. And the second part of that is actually creating a string that is basically the address of the receiver together with a salt. Salt is basically just something that allows you to make the encryption a little bit more dirty if you don't want to kind of create something, if you don't want your ciphertext to be similar between runs, and then people will be able to track who you're sending, not who, but like the fact that you're sending the message to the same person. And that's the actual line that actually encrypts. MIMC is a very, I would say, very unique type of encryption that best thing about it is that it's very friendly to if you want to run everything through a zero-knowledge system. Because zero-knowledge adds a bunch of calculations, especially if you're doing it on-chain. You want to have something that is simple to run, doesn't have a lot of multiplications, but actually also runs on the same prime field as the contract you're running it on. And I can expand on that if you have time. But basically, this is how it works. We encrypt all that into two statements. And I can show you how it works here and also tell you what you're actually getting out of it. So this is basically how it runs. And what we're getting is the addresses here, the addresses that we want to put in the event for people to know that they get a message, or somebody that has the public key to be able to say, this is my address. And what this gives you, what this code basically compiles to, is, first of all, it's a WebAssembly script that allows you to create those proofs, unique to your needs. And it gives you the WebAssembly binary, together with a JavaScript wrapper that allows you to put that directly into your web application. So you basically just run it with the messages or the things or the inputs that you defined previously, and it creates this binary string that you then use as proof. And obviously the second thing that it uses is the solidity logic that allows you to verify that proof. So these are the two components usually of zero knowledge systems, and this creates it right out of the code. And this is a demo, so it's a very kind of trivial constraint that we've put. But you can basically implement everything you want. You can implement like inclusion in a certain group of people. You can implement, what we're implementing actually in Grappa is that you actually pay the right amount of tokens. You can execute commands. You can say, okay, once you did that, now the price of that specific badge or that specific user goes up or down. And you do that in a privacy-preserving way, but not just that, in a way that doesn't require you to do all that in the back end. So it's actually highly, highly scalable. So yeah, so that's basically what you're getting from Circum. And that's kind of the most, like the central kind of scheme of that. And then when you want to send a message, put it up. When you want to send a message, what you're actually doing is starting with the pair generation. You sign a transaction. That transaction's, the output of that transaction, the output of that signature, excuse me, actually is the seed to create the pair that you have as a user. And then you create the shared secret. That shared secret allows you to then encrypt the message and send it and send it together with the proof that you've done everything right to the contract. Yeah, so now we'll go over some of the code examples of how you actually do that. There are a lot of, obviously, JavaScript libraries that make things a little bit more easy, but the tough part is in the integration between all of those. So we use a library that's called Elliptic. For short, it's EC. That actually allows you to create a key pair. And it creates it in an elliptic manner. So it creates it on an elliptic curve. What you see here is basically the generation of that key pair. You see the wrapper function. So ec.generate key pair, and you use the entropy, basically the seed. It's basically, what we're using is the input of the message. You'll see it in the next screen. So this is the initiation of the test. You create users, example users from Ether, and we tested out on hard hat. You sign message. That's kind of a generic message that we sign in order to create the entropy. And then you use that entropy in order to create the keys. Each user have 2 key pairs, as we've seen earlier. So yeah, so after we've learned all of, we saw how we can generate the keys, we see what we actually need keys. And I'm sure most of you kind of know what Diffie, Hellman, how you actually generate keys and why we need the keys in the first place. The more kind of official reason is that is Diffie, Hellman. Basically, Diffie, Hellman is the ability to transact something secret on top of a very public channel. So what you need as a setup is a generator number, a prime field, and then you'll be able to kind of generate your own private keys. Obviously, these are 256-bit numbers. I'm using this as an example, but if you generate a random number for each one of the users, you create a public key, which is basically taking the generator point to the power of that private key and modding by the prime field. You get different public keys, but then if you use those public keys together with the other users, if you use your own private key together with the other user's public key, you see that you're all getting at the same shared key. But you never exchange that shared key, and nobody else besides those 2 individuals actually knows that shared key. And if you encrypt based on it, then you actually are safe. The added kink for that in blockchain is that everything happens on an elliptic curve, right? So you don't need the generator point and you don't need the prime field because you're working on an elliptic curve that is defined by Ethereum, for example. Ethereum uses a curve that's called BN254. It has its own prime number. It has its own generator point. And when you use those, you don't need to even have the agreement or the setup. I'll be able to answer questions on that if you want, or at the end, or whatever. So yeah, so this is actually the lines that actually generate those shared keys. So you see I'm using my own message key pair, and using the function derive, this is from Elliptic, you're using it in order to create the shared secret. And we're using the shared secret from for each one of the user pairs. This is for test purposes, but that's basically how it's done. And then you encrypt the message, and encrypting the message, it doesn't matter what kind of encryption you use. We use AES because it's standardized, but that doesn't go through the chain itself. I mean, the encryption itself doesn't go through the proof itself, so it doesn't matter. The only thing that matters is what goes through the proof, and this is why we're using MIMC in there. Yeah. Okay. And yeah, and this is how we're actually calculating the proof itself. So remember I said that you're getting a wrapper for creating the actual proof. So you're getting this wrapper called calculator. You're calculating this thing called witness. A witness is basically a proof. It's kind of a mathematical kind of jargon that basically said this is someone who witnessed the truth, and then you kind of relay it to the chain, and that's your proof. But you're getting the wrapper. The wrapper actually has a WebAssembly backend. And then you run it on a library called snark.js that allows you to create this very short string that is basically the proof that you need for the contract. Yeah, and that's the kind of last part of the sending of the message. You prepare all of the inputs, and you prepare the private and the public inputs because everything is happening locally. Once you create that proof locally, you are able to then send it to the contract. You see we're doing it here with a simulated hard hat contract. And what you're expecting is an emission of an event with all of the information that we have. And that's basically how you send a message in the system. You're creating an event. An event is a public thing, but everything in it is encrypted and secure. And just to kind of complete things, this is how the decryption process works. You see that you're just reading the event. You're reading the arguments off of the event and then using that. Because you already have the private key, you're just decrypting it with an AES function. Yeah, this is just the encryption we're using. Just wanted to kind of put it up for completion of an encryption method that is actually safe to use under Snark, not just safe but efficient. And the reason it's efficient because you see how simple it is. It's basically take the numbers, just put it to the power of 5, add a number and the key, and do it 220 times. This is something that zero-knowledge proof easily understands, easily lends itself to that, and you don't need to have a very busy calculation that will cost you a lot of money. So yeah, so that's basically Grappa. I can say that these are the kind of problems we're solving. I just show you like a very somewhat simple demo example, but like I said, a lot of that is actually in the extension of what you can actually do in the zero-knowledge proof. We don't want to calculate too many things on the back end, so we calculate it in the proof. Everything is happening in the browser. I think it's a great thing. But just to give you some color, I mean, we have badges. We don't want badges to be airdropped, so this is another thing that we want to have in a zero-knowledge manner, like the ability to communicate to someone that we want to send them a badge, but they actually need to approve, they actually need to mint it from us in order to get it. So it will be permission, so we're using Merkle trees, but you have to do it in a Snark scenario, basically. Make sure, like I said before, that you're paying the right amount of token. So we will be able to pay the money without exposing the recipient, because you'll see a trail of money. So the way we are doing it is you're actually overpaying and then getting the change, but everything is working with commits that are working on zero knowledge. And it gets really complicated really fast. Attestation model, for example, this what I talked to you before about how a value is actually being propagated back to the issuer. In order to do it in a computational way, it needs to go through the zero-knowledge proof as well. So then you ask yourself, how do I credit different issuers? Do I credit them homogeneously? There are a lot of aspects of dynamic programming, economic models, grading algorithms that goes into in here. And yeah, trust me, there are a bunch of other stuff. So thank you very much. Be happy to answer any questions. Yeah, so the tokens I was talking about, basically, we call them badges, but it's basically a very simple, not very simple, it's like an NFT type asset, but it comes with a lot of logic behind it. The process of getting it, like we're talking to a lot of issuers now, we're onboarding them on the system. A lot of that is actually people that want to give reputation. A lot of it is actually, now we're actually looking into a lot of events. Events could be an event like this, could be a hackathon, it could be something that you can uniquely attest to someone's singular achievement. And because it's so reciprocal, because the issuer actually gets a lot of benefits from it, that a lot of people, a lot of events actually seek, so they actually are sending those tokens to their users, constituents, however you want to call it, but they're doing it through the system. You can do it for the system, you can send something to a certain, much like you send a message, you will send something that is similar to, I want to give you a token, and then you need to choose to receive it. And when you choose to receive it, you actually get it as an asset, but actually the fact that I send it to you as, you can actually just use that as well. But not to complicate things, it's like the way of, giving something out as a message and then following up a cascade on your side. That's a great question. And the way you're doing it is because everything is governed by money. Not money, like tokens. Tokens, obviously, if you're working on blockchain, then everything is money because everything is convertible. But you're disincentivized to do that because not all the money here, not all the tokens actually go to Jane. Like if I'm Jane and want to scam the system, I need to understand exactly where the money is going to. So if I want to buy reputation, we need to make it economically unviable for you to do that. So it could be through like burning some of the tokens, right? And then what we're officially are doing is putting a price on reputation. As long as that price is lower than how you organically are going to achieve it, then I think we're good. Then I think there's like disincentive to actually do that. So you're getting something in return. You're basically buying attention, right? Because you're sending a message to Jane, you're paying the price that Jane currently has for her time. So that's the proxy for reputation, not exactly the reputation, but your willingness to pay that price or to pay that in tokens actually allows us to understand how much Jane time is valuable and how much all of the things she's done, or all of the issues that actually vouch for her are valuable as well. And as a singular transaction, you can think of it as just a gradient towards value discovery as a whole. So what we want is a lot of transactions like that that converge to allowing us to understand what is the value of badges. What is the valuable badges for issuers, for engagers, I'm sorry, and what are people's kind of true reputation. And the reason I said in the beginning that we haven't seen a system like that because you're not seeing that in real life as well. Like if you have a degree from a certain university and somebody wants to hire you, there's no feedback loop that goes from someone who wants to hire you to that university. Now, we live in an age that universities are phasing out and courses are coming in and even self-taught skills are coming in. So what you actually want to achieve is that the person who wants something from you, the person who wants to hire you to do something, can actually affect the reputation of the person who either vouched for you or actually gave you those skills. And that's kind of the feedback that we think is missing. That's what I said in the beginning as alignments that are missing in the world. And when you think about this, how the world works, but it's just not working in a digital way like that. Everything in the digital world works through self-reported achievements and usually macro achievements. So that's basically what we're aiming at. Hope it answers the question. Yeah. Yeah, so if I understand the question you're asking, like if I can play multiple roles in the system, I'll basically be able to create something that is somewhat fake, and therefore I'll be able to create value or reputation for myself out of nowhere. And the system, because it's balanced, or we aspire to have it balanced in a way, that things like that won't float to the surface. For example, if I'm an issuer, I need to convince people to actually take my badge. If I'm issuing a fake badge and people take it, I might be onto something, right? It could be that I'm actually giving something valuable to people. And people are not obliged to get it because, remember, they're giving some of their value to that issue. So you as a user who received that badge needs to believe that there's something out there that actually contributes to you. So that's kind of the back incentives that are supposed to filter things like that out of the system. Now, I know that things like that are like very theorized, but when you think about, I mean, all we can do is kind of draw the incentives and think about like how we incentivize people to the right behavior, and then see how it works in real life. But because we see similarities like that in actual people interaction, we actually believe that that's the way to go. But obviously, there are going to be a lot of things along the way that we're going to find and fix. Can't see anything. Is anybody? No? You have a better viewpoint over there. Oh, yeah, over there. Yeah, so that's a great question because that's all the industry is talking about, like how long it will take you to prove something. Currently, it's not prohibitive for us. It's a few seconds to just prove a certain message. There are a lot of optimization that we haven't took yet, but we are not seeing something that's prohibitive. And if it's prohibitive, there are a way to remedy this. Some of that is for relayers or people that actually, like entities that calculate the proof for you along the way. But for the needs that we have right now, we're actually pretty fast on proof generation for the sending side. And the receiving side, the proofs are a lot smaller, so we're not worried about that. But that's a very good consideration to take into account if you're building a system with this architecture. That's it. Out of here. Okay, thank you very much.